first we should talk about something that has been discussed in other videos before, but the bisection method, which is that you start with 2 points and you say, I want to find what's here. You say, this is too low, this is too high. I go into the middle. This one's still too high. I go to the middle. This one's too high. I go here. Now this one's too low, so I go here, and I keep dividing over and over. And this is a very simple method and can be used with basically anything that's an increasing function, which this is. And if you're wondering why I'm so confident that this is an increasing function, well, you're making the network bigger when you make x bigger. There's no way you could make it so that the maximum flow gets smaller. But there is a problem. It might not ever find the answer. And there's an example of this that's actually surprisingly easy. So let's look at y equals x, and we start with 0 and 1 as our endpoints. And we want to know when y equals 1/3. Obviously x equals 1/3, but if we did it, we go, okay, we'll look at these. 1/2. 1/2's bigger than 1/3. Okay. Let's try 1/4. 1/4 is bigger than 1/2. Okay. 1/2 plus 1/4 is 3/4 divided by 2. Let's go try 3/8. We're never going to get to 1/3 because 1/3 cannot be written this way. But we can do a little better. We've modified bisection. Now, I didn't totally discuss them last time, but these little gray lines, those are the theoretical lines of each cut set. And there's this yellow line, and that's the one where our low is. And we can actually figure out, in this case, the slope of this line to use it to help. So we can use it to tighten the bounds. So let's say we were looking for well, I know that it can't be any earlier than here because that's the fastest it could be. Also, I'm very sorry that line is not straight. So it clearly can't be anything earlier than there. And that's because this function's convex. If it was concave, this wouldn't work. The convexity, you can think about it as being, if I was considering building this function up and I found cut sets and I removed them, found cut set, remove, found, remove, it would be trimming corners every time or doing nothing. We can't get something that will go like that because this line is smaller than this line, so we can't get any concavities. We also only need to do max flow problems. And this seems weird at first, because the max flow problem basically is sampling the function at a point. You might wonder how we get this slope from a max flow problem. We'll get there. And we're guaranteed to do it in finite time. The actual maximum amount of time it takes can be really long, but there's only finitely many cut sets, even if there's a lot of them. So we can't get into this situation where we're trying to take halves until we get to 1/3. So let's look at an example. In this case, we have n xns plus nb. And that way we can look at this all on one thing. Now you might recognize nb from something, and that was intentional. As you can see, all of these capacities are based off of this x value. And I'll give you a little hint. X equals 5 for the thing we're looking for. We're looking for what's the smallest x so that the flow from the source to the sink has value 20. You can pause right now and compute what they are when x equals 5 and see that it works. But we don't know that. Well, first we want to look at, okay, what if x equals 0? Well, we only get a value of the flow of 1. And you might be like, what about all these other ones? Well, they are all feeding off of it. So we only look at the arcs that leave, and we get a 1 and a 0. So that's the best flow on NB. What if there was no obstruction? Well, on NS, we get 1 and 2. The base flow is 1. The flow that we get from adding NS is at least 3. I'm saying at least because, well, we'll see. So we know that, so this is how we're going to calculate our high point. The reason why we can say this is we can always take this flow and add this flow times x and get a valid flow on the result. It might not be maximal flow, but it is a valid flow. What we say is that we're looking for something where the value function, this little v of h, it's useful to give it a little name like this, is at least 20. So we don't know what it is. Well, we can go ahead and we can say the high point, 1 plus 3 times the high point is 20, and we give this little xh a name, saying that that's our high x. That's our, on the bisection method, that's the one that's further away. So we know that whatever the answer is, it can't possibly be bigger than 19 over 3. Let's compute the low. So we have an interesting network here, and you might be like, what's up with these infinity symbols? And where did this come from? Well, let's start by looking at this. Notice that the capacities of all the arcs on this one that aren't infinity are here. Now, what's the thing with all the ones that are infinity? Let's compute the residual. So the residual here, well, that's 0. The residual here, that's 2. The residual here, that's 3. This one's 2. This one's 2. Notice that everything that has a residual that's not 0 gets an infinity. And that's because when you're adding a very small change in x, the amount left over is infinite, in giant air quotes. I go into this in a lot more detail in my paper, but you can think about this sort of process as being valid. And you might be like, well, how do we know that we're not getting something that's infinite? Well, if we got something that's infinite, that means we didn't do the maximum flow on NB. We didn't fill up the whole flow. So that seems reasonable. So we compute our maximum flow and we get 4. And this is the slope, because if x is small, you could add x times this flow to the base flow and get something that works. However, if x is big enough, these aren't really infinity, so it wouldn't work. And it also must be the highest of everything, because as we get further along, more and more of these useful connections will be filled up in their base flow, so there'll be fewer and fewer infinities. So if we use this, if we assume that it's just a line going from that point onwards, we're overestimating the value function. So when we flip it around, we're underestimating where it is. So we get VXL. And we know that the value at XL must be less than or equal to 1 plus the slope at that point, which is here is 0. So we get 19 over 4. And now we do bisection, the arithmetic mean, and we get this. I'm very sorry that it comes out to these terrible fractions. The value, however, is 21 and 5/8, and the median thing is we're at 19 over 3 plus 19 over 4 all over 2, and you can figure out what that fraction is, but I don't really care right now. But I did this all correctly. So we know that, okay, it must be, whatever our goal is, it's between XL and X middle. Whatever answer is, it's between those two. Well, now we should look at X low. The flow at X low, so this is X is 19 over 4. And we say, okay, we get that it's 19 and a quarter. So we're close. Let's compute the derivative. So again, what we do is we look at this, and this one doesn't get to be infinity because it filled up the whole thing. This one doesn't get to be infinity. This one doesn't get to be infinity. And this one doesn't get to be infinity. Now all the other ones, and those are all X slope. Hey look, we actually get something that looks pretty good. So let's see. I think that flow is 3. Yeah, value is 3. So now we can compute the low estimate. Well, it's 5 because 19 1/4 plus 3 times 5 minus 4 3/4, which this is 19 over 4. Well, that's 20. So again, the same idea. We have this little minus the x we're starting at, and our high estimate is also 5. This comes out because we compute that 19 1/4 to 21 5. The other thing is that the slope is already the lowest possible, so we know it's the same. So there we go. Some of the numbers are a little hairy, but we got there very quickly. But why did we do all this? We reduced the utilization from some whatever naive technique we had. Let's say we just took the flow on the scaling network and we just scaled it up till it was 20 and plopped it on top of those obstructions. Well, whatever it is, we found the best one. We found the lowest X, which in turn means the lowest utilization. But we didn't compromise the value of the flow. So that's nice. In fact, it sounds useful. Where is it useful to reduce the utilization but keep the flow value the same? Aha! Now we can update the U-flow with this flow we found. We were using flow because it was a flow on the network we were working with, but in the original thing, we don't know if it fit, so we call it a U-flow. And the obstruction is all the other U-flows we neglected. We started this whole thing by saying, just lump everything else together. Now we can unlump everything, and that doesn't change the utilization. And by replacing whatever flow that was there before with this one, well, it improved it. So now we can try another flow. Because the flow we updated changed, the environment, the surroundings of all the other U-flows are all different. So if one couldn't be optimized before, now it might be able to now. And this comes to AFFPAA. I have on screen what the acronym stands for. It's a lot, but we've already walked through a stage of AFFPAA. Now, we ignored where the other flows came in, and in that sort of network, it's kind of weird about asking what kind of flows would have created that load in the first place. But we went through, we saw a flow, we expanded on it, and we improved. And each stage, we improve one flow at a time. Now, this is useful because there are some very, very good algorithms for doing one flow. In fact, there are ones that are computationally crazy fast. The one I showed here was just one of the simplest ones to explain, the simplest to convince you that yes, this is a maximal flow, but there are some that are very, very well optimized. And our initial condition, because this is a progressive approximation algorithm, we just start with the max flow, so we ignore any interactions because we haven't dealt with them yet. But there's some questions. First of which is, does it always come to an end? Because every time you change one flow, it changes everything else around it. Do you always keep getting better? Can you always find another way to get better, to squeeze a little bit more out, Does it always end with the right answer? If it goes to completion, is there not some better way of doing it that it missed? This can be a real concern with greedy algorithms like this, that's always trying to do what's locally best. Now, there is a technique called linear programming that works with sets of linear equations and inequalities, but there are some caveats, such as they can be pretty slow. Some of the algorithms can be very fast, but their worst cases can be very, very slow. And there's a lot of things where it doesn't get to take advantage of, like knowing how flows work. So you might have situations where flow conditions are violated in the middle. And if you're in a situation where you need to get at least a pretty good answer, having something that might not be an answer midway could be a huge detriment. If you're, say, routing internet traffic and you need this much from this person, this much from this person, it's much better to have a pretty good answer right now than a perfect answer much later. thank you. I don't know how many videos this has turned out to be. It's been a lot of recording time, but you can always ask your questions in the comments, maybe on my Twitter account, though I'd rather you just send me comments. And I don't know if I'll do this again. Maybe if I write another math paper, I'll do something like this. Or maybe I'll do a follow-up on this. Who knows? Anyway, I am not looking forward to editing all of this. Bye.